Welcome everyone to our Boros Media Tea Time Talks. We are part of the Interpol Young Academy, and we aim to provide young researchers the opportunity to present their work in this platform. So we are here today for the 54th session of the Tea Time Talk. And we will have two speakers from Europe and USA. So please welcome our first speakers, which is Negar Shahsavar. She is a PhD candidate at McMaster University in Canada. So she works on reactive transport in confined geometries under the supervision of Dr. Ben Gonzalo. Sorry for my pronunciation. So prior to this, she earned a bachelor degree in petroleum engineering from Sharif University and a master degrees from Shiraz University in Iran. And today she will present her work on precipitation flow in confined geometry with a focus on mixing, fingering instabilities, and deposition. So Negar, first, we want to thank you for agreeing to present your work, and the floor is yours.
Thank you, Sarah, for the introduction. Hello, everyone. I'm Negar, and I'm last year PhD student at McMaster University, and I work under the supervision of Dr. Robin Zhao. First, I have to thank the Boros Media Tea Time Talk group for their invitation and giving us the opportunity to present our latest results. So today I'm going to talk about the precipitation flow in confined geometry, mixing, fingering, and deposition. This work has been done in collaboration with Dr. Ruby Fu from Caltech. Reactive transport involved with precipitation and deposition of particles is a common phenomenon in many processes. For example, in CO2 sequestration, when carbonate-rich fluid is injected underground, it triggers precipitation of carbonate minerals that eventually deposit in the pore space and change the porosity of the formation rock. When we have reactive flow that generates precipitation and deposition, it can alter permeability and porosity of the porous media both in time and in space, which leads to significant increase in pressure drop and decrease in injectivity. So it is important to understand how these processes take place. Laboratory studies show that the precipitation flow is a complex system, which is due to highly nonlinear coupling between advection, diffusion, and reaction. So for this reason, people have studied the precipitation flow in simple geometry, such as Hellas-Shostal. Hellas-Shostal provides us a simple but effective platform to study these highly nonlinearities. For example, in the studies by Nagatsu et al. And Kim et al., they have shown that in Nagatsu et al. And Schutzer et al., they have shown that even in a complete homogeneous Hellas-Shostal, the interactions of different parameters can generate a wide range of precipitation patterns. So we wanted to understand these processes a little bit more. We studied the reactive flow dynamics of calcium carbonate precipitation in Hellas-Shostal. And the key differences in our experiments, in our studies with the previous studies, is that we used much smaller gap thickness of 100 microns compared to 500 microns in previous studies. And we also quantified the gap average concentration of particles by analyzing the local light intensity. We observed that precipitations are generated at the interface between the reactants, which form a radial precipitation band that moves outward with the flow. Here, the color map is showing the gap average concentration of precipitation, and the brighter color shows more precipitation in the gap. Based on the color, we can clearly see that at higher injection rates, we have a larger precipitation compared to lower injection rate. And also at higher initial concentrations, we have brighter patterns, which means more precipitation in the gap. The injection rate has a significant control on the concentration and spatial distribution of precipitates. For example, at the same initial concentration at low injection rate, precipitates are small and they are deposited uniformly all over the cell. But at a higher injection rate, larger aggregates are formed that deposit as discrete clusters along the radially outward direction. And also, we can see clear signs of viscous fingering at higher injection rates. Viscous fingering of precipitation flow has been studied in the past. Researchers found that particle enrichment in suspension flow can yield to viscous fingering because of the low local mobility of the suspension. For example, in the experiments by Tang et al. And Kim et al., they observed that in the flow of dispersed particles in oil in helical cell, we can see viscous fingering at the interface. These fingering patterns are very similar to the fingerings we observe in our experiments, but the difference is that the particles in our experiments are actively generated in situ as a result of the reactions, and we only see them in high injection rate experiments. The reason why we observe viscous fingering only in high injection rate experiments is twofold. The first one is that when we have a higher injection rate, we have high shear stress across the gap, which helps the precipitate particles to overcome the interparticle repulsion forces and form larger aggregates that increases the effective viscosity of the suspension. And the second reason is that the higher velocity of displacement accentuates the viscous fingering instability. The viscous fingering not only controls the amount and spatial distribution of particles, but also the rate of their production. In our experiments, the scaling of total amount of precipitation is held for different concentrations that we used in our experiments, but they are changed as we change the injection rate. So in low injection rate, the total amount of precipitation grows diffusively in time as t to the half, while at high injection rate experiments, it grows linearly in time. And for the intermediate injection rate, we have linear scaling at the beginning, and then it evolves as diffusively in time. And the transition in the scaling corresponds to the shutdown in viscous fingering. Viscous fingering enhances precipitation production rate, and the reason is that it generates a recirculatory flow inside the finger, which brings a fresh fluid, fresh reactant to the mixing zone and enhance the mixing and reaction. Modeling of precipitation flow has been the focus of many researchers. The existing model use an advection diffusion reaction equation, and they assumed that the viscosity changes exponentially with the precipitation concentration. These models did not capture the variety of patterns observed in experiments, and also they did not capture the deposition and temporal scaling of total precipitation production. Based on our experimental observation, we think the existing models can be improved by incorporating a more realistic rheology and deposition models in order to capture the behavior we observe in the experiments. The local shear rate at the band is going to control the mobility or the effective viscosity of the suspension because of the particle agglomerations, and also particle deposition on top and bottom glasses of helical cell can affect the local permeability of and porosity of the cell. So in our model, we solve for the evolution of B, which is the available gap thickness for the suspension flow to happen. In our model, we start with the mass balance, and our mass balance takes account in evolution in B, and we have the transport equations that take account of the consumption in the reactant concentration due to reaction, And it also accounts for the precipitation, the formation of precipitates, and their deposition. So in the transport equations, we have three dimensionless variables: the Peclet number, which is the ratio between the rate of diffusion and advection; the reaction dome color number, which is the ratio between the rate of reaction between reactant A and B and the transport; and we have the deposition dome color number, which is the ratio between the rate of deposition and the transport. Eventually, we update the gap thickness as a function of the amount of deposition formed. So we solve the three blocks of equations sequentially in our model, and we have the same boundary conditions as we have in the experiment. So we have constant injection rate at the center of the cell, and we have open flow boundaries at the perimeter of the cell. From our experiments, we could see that the effective viscosity of precipitate suspension should be a function of both local concentration of precipitation and also shear rate. So intuitively, increasing the concentration increases the effective viscosity, but also increasing shear rate increases the viscosity due to formation of larger aggregates. So in order to model this complex rheology behavior, we used a modified cross model. And for the deposition, existing studies of suspension transport show that the rate of deposition is proportional to the concentration of precipitation in the flow. Additionally, people have found that there is usually an onset of precipitation concentration, below which there is very minimal amount of deposition. So to capture these effects, we model the deposition using a modified first order deposition. And it depends on the concentration of precipitation, and also it includes a cross flow function that takes into account of onset concentration. The simulation results show the same behavior that we observe in the experiments. So at low injection rate, we observe that the precipitation band is stable and small particles deposit uniformly all over the cell. While at high injection rate simulations, the same as experiments, the band of precipitation is unstable and we have viscous fingering. We also see that precipitates deposit along the finger side. However, in our model, depositions do not pinch off into discrete clusters because we did not include surface tension effect in our model. So beside the precipitation pattern, our model can capture the evolution in the precipitation rate. So the same as experiments, in the simulation, we see that in higher injection rate cases, the total amount of solid in the cell evolves linearly in time, and in lower injection rate cases, it evolves diffusively in time. So we wanted to test our model beyond the set of experiments we have performed. So specifically, we used our model to simulate the experiments conducted by Schutzer et al. They conducted a calcium carbonate precipitation in a Helle-Shaw cell with a much larger gap thickness, in this case 500 microns. And they had different initial concentrations of reactants. From bottom to top, they increased the initial concentration, and from left to right, they increased the ratio of initial concentration, or beta, which is the ratio of the initial concentration of calcium chloride and sodium carbonate. And amazingly, we can see that our model can capture the variety of the precipitation patterns that goes from surface filling to hollow tubes. And this is the movie of transition from surface filling patterns to hollow tubes as we increase beta in high Doppler number regime. So to summarize our research, we conducted a simple precipitation flow in Helle-Shaw cell, and we observed a diverse range of patterns, and we observed that in higher injection rate experiments, we have viscous fingering and we have larger precipitate particles because of the effect of agglomeration, and we observed that viscous fingering controls over the precipitation rate, and it evolves as t to the half in the absence of fingering, and total amount of precipitation evolves linearly in time in presence of fingering. And we incorporated a rheology model that captures the precipitation concentration and shear rate, and also a deposition model into an advection diffusion reaction model framework. And we could predict a precipitation pattern and a precipitation rate that we observed in the experiments. Thank you for listening to my presentation, and I'll be happy to answer your questions if you have any. Thanks.
Okay, Nadar, thank you for your wonderful presentation. And those of you who are watching this, please, if you have questions, write in the chat box, and we will deliver it to Nadar. And while people are formulating their questions, I had a few questions from myself.
Sure.
So as an experimentalist, I was wondering, you mentioned that you try to estimate the gap between the helical cell plates by estimating the light intensity. So can you briefly explain in little detail the process you took to estimate the gap between the plates?
So we estimated the gap average concentrations. If I go to the... So we record the experiments by the camera from the top, and these precipitates, because they block the light, we can measure the local light intensity, and it gives us it's a cosine function of the amount of precipitation in the gap. So when we have more precipitation in the gap, it blocks more of the light. So we can see that it decreases more. And by doing the image analysis, we can have a semi-function of how much precipitation we have in the gap.
So you had prepared the precipitate with a known thickness to as a standard to use as a calibration?
Yes, so we actually, the way that we analyzed the image was at each time step, we subtract the current image from the reference image, which is the cell without any precipitation, and it has the maximum intensity because there is no blockage of light. And then we normalize that by the highest value of the precipitation, which is like the parts that we know that they are not moving. It means that they have filled the whole gap thickness in higher injection rate experiments. And then we could, we have like a semi-function of how much precipitation we have in the gap.
Okay, thank you. And while you're answering my question, there are some questions in the chat. So two from Ali Reza. So thank you for great presentation.
Thank you.
Did you anticipate any effects from the roughness of the surface on the patterns that you observed?
No, we did not. We did not take account into the effect of roughness of the surface, and we assume that the precipitations are homogeneously distributed over the glass surface if they are generated at any locations.
And then there was a second question. Also, was your model able to capture the accurate time scale of precipitation for different flow rates? I saw a time difference between the simulated and experiment.
Yes, there is a little bit of difference. So the model can be improved. Actually, the rheology model can be improved, and it has many capacities for improving that. That could be an environment that we could work on in future. But we set the tuning parameters of the rheology in a way that we could capture the best transition from having fingering to not having fingering, and this transition at exactly what location happens. But it still could be improved.
Okay, so we don't have any more questions in the chat. So I think we can thank Negar for her great presentation and move on to our next speaker.
Thank you.
Thank you. So our next speaker is Milad Naderloo. He is a postdoc in geomechanics and applied geophysics at TU Delft, holding a master's degree in rock mechanics from the University of Tehran. His expertise lies in induced seismicity, fault mechanics, passive acoustics, and rock deformation experiments. So today he will be presenting on experimental and numerical investigations of sandstone deformation under cycling loading relevant for underground energy storage. Milad, floor is yours.
Just double check.
Yeah, we can hear you.
Yes. Okay. Thanks for inviting and giving this chance for this talk. So hi to everyone from all around the world, from the meeting cabin inside TU Delft. I couldn't find another room. So today I will present you part of the research from my PhD. I slightly changed the topic and brought new things than the one you advertised, which is about fault reactivation and rock deformation mechanism under stress, pressure, cycling, and relevant for underground energy storage. So before starting, I want to show one of the, let's say, important slides here. You can see all those researchers or supervisors in the top row, Auke, Anne, from the experimental side, and Heidi and Yander Janssen from numerical and mathematical side. And then you can see this fellow PhDs and master's students in the bottom row, that they are all involved in this research, and I wanted to thank all of them. So then I'll start my talk with a brief introduction just to bring you to the game that we all know these days. We're talking about it, this climate change concern, all we have, and then we are proposing solution by moving toward renewable energy, different types of renewable energy. But it's not easy. We all know scientists in different fields challenging to overcome this obstacle. There are many concerns, like season, because you cannot find in, let's say, in winter, nice solar energy, a lot of solar energy, or the location. Some locations are not really, let's say, proper to produce wind or solar or let's say water power energy. And then another point is storing it. What is happening is you're producing a lot of energy during the summer, and then your demand this winter is high, and the discrete doesn't really match. Then how to really overcome this? And then to wrap it up, a successful transition toward cleaner renewable energy needs this effective large-scale storage. Like, we can store energy there when we have extra energy, and then we can use it when demand is high. This is one of the big challenges. So geoscientists proposed...
I'm sorry, Milad, I have to interrupt you. It seems that the slides that you are showing is not really changing on the screen, and we're still seeing your introduction slide.
Oh, you don't see?
No.
You don't see?
Maybe if you share your slides, then it will solve the issue.
Let me do this. Let me do this. Sorry. Till which slide you? Okay, I start from over. This. I have this. I stop screen and.
Just Milad, just an advice: put your slide in full presentation mode before going to sharing your.
Yeah,
screen.
I did okay. That. So I share the screen. You have it now?
Yes, now we have it.
It is changing.
Now it's changing. Yes, perfect.
Okay. Till when you followed me, then I can.
We just saw the initial slide.
Just this one.
Yes.
Okay. Then I was introducing all the people involved in this research. Then I already said that. Then I skipped it. Then I talked about this, let's say, energy transition and what is the concern there. That's what can be the solution that we can, let's say, move toward cleaner renewable energy, then we need storage. We need to store energy in a time that we have extra energy, and then we're going to use it in a time that we need it. So the geoscientists proposed that we can use subsurface, we can use depleted gas reservoirs, we can use salt caverns to store energy there. We can store compressed air. We are thinking about storing hydrogen there, using it for the geothermal purposes, and then previously we used it successfully for gas storage. So this is one of the solutions that we can store in large scale, but it's not easy when we look at it, because what is happening when we are using our depleted gas reservoir as a energy storage? We are injecting there when we are needing that, we're taking it out. So what is happening in this process? We are applying a cyclic condition on our reservoir. So it's like a dynamic condition with different frequency and different amplitude that we are imposing to our reservoir. So, and then what is happening? If we expose materials to cyclic loading, they're gonna behave differently. It's not just load, is also temperature by injecting your fluid. There is also chemistry there can play a role. But let's just focus on the mechanics here, that by applying the cyclic condition, you are imposing change on your effective stress that can drive fault reactivation and subsidence and uplift, which is a big concern nowadays for, let's say, energy storage. So thinking about this as an experimentalist, we think how we can help there. So in a simple way, we take rock sample analog to the reservoir rock, and we want to do experiment on it in a cyclic condition. And what are those important parameters that can play a role to see how our reservoir rock behave? One of them is frequency. Like you want to inject and deplete your reservoir in future, your hydrogen future storage, which is can be daily, can be weekly, can be monthly. That is important. Or the amplitude. You are storing with the same amplitude and in depleting with the same amplitude. But after 2 years, you see, city is bigger, we need more energy. Let's store more and let's inject more. Then you increase the amplitude. That's going to play a role. Or the reservoir that you are working on, that is it high stress regime, low stress regime, how deep it is. So these are the important things. Then this research, we try to answer that. So for that, what we need, of course, experimental setup. This is our loading system that we put this nice cylindrical Redfelser sandstone, which is from Rottlingen formation, inside our pressure cell. We are providing confining pressure with our ISCO pumps, and then we are providing sigma 1 principal stress with this loading machine here we have. And then one technique that here we are using is acoustic emission technique, which simply we are listening all those micro earthquake happening inside our rock that can be inelastic deformation in the form of micro crack growth, pore collapse, or friction of the grains on each other. They are producing wave. We are listening to them by converting to the signals, and then we analyze to see, how that event looks like. So this is our experimental setup. And then after setting up in our setup, what we need the experimental protocol. So this is our experimental protocol and how it looks. We have our axial stress in this side, or a principal sigma 1 stress, how you can say it. And then we increase the axial stress and we bring our sample to failure while we have our sigma 3 or confining pressure 10. So we want to see different stages of failure. First, we have a bit of initial stage of loading, a bit of pore closure, micro crack closure, and then we get in our elastic or linear zone. And then after that, slowly we are getting out of the linearity, and then this is our brittle yield point. I say this stuff just to grab your mind to how one rock can, like our sandstone, can behave under loading. And then we use this to design our protocol. We want to apply cyclicity in this stress level. It's a 38 megapascal. or we want to go do cyclicity in a high stress regime, 85 megapascal, which is slightly above our brittle yield point. And then this is how our stress, cyclic stress waveform looks like. You may say maybe in reality, when you are injecting or depleting your field, can be like a sine wave, can be square wave, can be in a different shape. But here we just use the triangular waveform shape cycles. And then apart from two stress regime, here we are using also three frequency, high frequency, medium, and really low frequency. And then we are using two amplitude of the cycles to see how that affects or impacts inelastic deformation, or let's say in a general way to say how it compacts our reservoir rock. So I directly jump to the, let's say, cherry on top of the cake result that gives a total picture of the result. Here in the left-hand side, we can see total axial inelastic deformation. Again, I say how much we could compact our reservoir rock is here with different amplitude and different frequency. Of course, in the first look, as we expected, the larger the amplitude, the more damage you are inducing inside your sample, and then the higher the stress regime, again, the more inelastic deformation. But what is really important, and then we observe that if you lower your frequency of the cycles, you are inducing more inelastic deformation in your system, and it is really pronounced in the even elastic regime. So let's look at by detail to what happens for inelastic deformation per cycle. We applied 8 cycle. This is from above brittle yield point, and this is a blue brittle yield point. What we can see, the main inelastic deformation happening during the first cycle. If you are going to start your energy storage, the first cycle is responsible for the inelastic deformation that happening in your system. But another thing that is important here to mention is how they behave by increasing the number of cycles. We see if we are in elastic zone, low stress regime, it's slightly flattening and there is no increase in elastic deformation. But when we are in higher stress regime, still by increasing the number of cycles, we are inducing some inelastic deformation. And then I put all the experiments here to have a whole picture of what is happening by increasing the cycle. Focusing on the top figures, we can see when we are above brittle yield point and we have low amplitude, by increasing number of cycles, again, they are merging toward each other and flattening. But when we have, let's say we are in a high stress regime and we have high amplitude, and especially this green one, lower frequency, there is some sort of time-dependent process going on, like creep, can be viscoelastic, that by increasing the number of cycles, still we are inducing inelastic deformation. But if you go to the blue brittle yield point, let's say safe zone, or lowest stress regime reservoirs, then after 8-10 cycle, we can see that inelastic deformation doesn't add into system. So I also mentioned that we use acoustic emission technique here, that as you can see, we have here our plot. In the left-hand side of the plot, we have amplitude of those events we are receiving. We listen to those events and we see what is the magnitude or amplitude of that event that I'm receiving. And we can see by increasing the number of cycles, the number of events that happens is dropping. And another thing is all those big ones, these dots, with higher amplitude are happening in the first cycle, which is kind of correlating with this one I showed you, the first main inelastic deformation happening in the first cycle. So then they are nicely correlating. So this is what is we are observing in the lab, but of course many people may say, you know, this is just homogeneous, nice, intact rock you are testing. Of course, then we need to come up with constitutive models that can capture all this observation that we have during the experiment. Then we can think about upscaling it. So this is the constitutive model that we propose that can capture all those deformations that we observed experimentally in the lab. When we are in the blue brittle yield point, you can see in this plot, we have black one is the modeling, and then the dotted red one is experimental, that they are nicely matching with each other and fitting with each other, even with the different frequencies. Because of lack of time, I don't go in the detail that different models that we use to come up with the constitutive model. Here you can see like Camp Clay model, hardening, softening, and then creep. Also above brittle yield point, we can see we can nicely fit the experimental data with our constitutive model. So apart from the intact rock that we tested there, we have also faulted rock, faulted medium inside our reservoir. So which is changing the game, is totally different. So now we're gonna see if you have a faulted medium, then how pattern of injecting can help to change the, let's say, behavior of your rock. So here, I don't want to go into detail of this protocol, but in general, what we do here, we bring this faulted medium to critically state condition. What that means, this faulted medium is ready to sleep. If you inject a bit, increase the pore pressure there, it's gonna slide and bang, earthquake happens. So here we wanna see how 3 different injection patterns monotonically. You have a reservoir, you want to say the operator, inject there monotonically, or you can say, inject, wait, and again inject. Then we call it a stepwise. Or we can say, inject cyclically, because we want to try to come up with a solution that we don't want to induce big earthquake there. We want to see how we can inject down there into our subsurface hydrogen for the geothermal or compressed air, that we are avoiding big earthquake, or we can replace big earthquake with a couple of small earthquake. So here, with all the injection patterns, we're gonna reach 19 megapascal pore pressure, and then the confining pressure, sigma 3, is 21 megapascal. It may look a bit messy or complicated graphs, but I just draw your attention to the black one, which is pore pressure that we are increasing in our system in a monotonic way, pore pressure that increase the stepwise, and then pore pressure that we increase in a cyclic way. And then the red one showing is slip velocity, what it says, like how fastly your fault moving. And it's really important. If it moves faster, then you have a bigger earthquake. And if it moves slower, and then you have a small earthquake. So here we can see in the monotonic one, we have acceleration and slip velocity, and then it gets constant or stable. But the other ones, we see episodic number of slow sleep, or let's say nucleation of the earthquake, which we don't want. And then another thing that can capture the eye is that maximum slip velocity that happening in cyclic injection is more than happening in monotonic one, which is, okay, it's showing now is dangerous if you want to use cyclic injection in the pros media, faulted pros media. So I captured all those important, let's say, parameters, like number of earthquakes you are producing, the energy of all those earthquakes that you're producing, and then maximum slip velocity, or B value that shows how much you have large earthquake or how much you have small earthquake. Then capturing and wrapping up all this stuff, it shows the maximum peak slip velocity and total radiated energy resulting from cyclic one is more than monotonic and stepwise one. And then that tells us if you are going to inject, this is of course fundamentally in a lab scale result, that if you want to go and inject in a faulted pros media, you should be careful if you want to do it in a cyclic way. So then I wrap it up with the conclusions that we saw inelastic deformation occurs even in an elastic zone. We call it elastic zone, but it's just linear zone. There is an inelastic deformation there. And then amplitude, stress regime, and the frequency of the cycles can affect the formation of our reservoir. And then our constitutive model could, let's say, nicely capture all those deformation we observed in the lab. And then the last part of presentation was about comparing different injection patterns. That monotonic one showed that more potential to mitigate earthquakes gonna happen in our reservoir. So yeah, by that I thank you all and finish my presentation.
Yeah, thank you very much, Milad. Very interesting job, very interesting presentation. I personally got a question, and meanwhile, maybe the audience can type down their question in the comment section. Like a bit basic question: how does this acoustic method work? Like, how do you differentiate between different phases of your experiment? How do you differentiate between the microfractures and then like bigger fractures, elastic parts?
Yeah, so that's a good question, because you cannot 001 always come and say, you know, it's like an earthquake, because we call it micro earthquake. Of course, we do record from the, let's say, the stage that we really want, and then we discard those stages that we didn't want it. That's the first step. And second step is when you have this event and signal, you can analyze it, you can locate it and see where it is coming. And then even if you have more sensor, you can see if it was collapsing of the grain, if it was the, let's say, shearing of the grain of the plate, or is it mixed mode. Also, it has this capability to come up with the moments in tensor inversion and then see what is that event coming from, as you ask.
All right. Have you ever cross-correlated, like after that you perform experiment, maybe doing a CT or something to see whether you guessed right, like there has been a fracture or something?
Yeah, unfortunately, yeah, we didn't do that, but similar work down in Utrecht University. They also, Harriet, what I have seen, they did, let's say, cyclicity in elastic zone, not bringing sample to failure, just in elastic zone, and they took and they saw, let's say, what is the main mechanism is like you have your quartz grain in sandstone, and then between them clay coating them, and then this squeezing of the clay is the main let's say mechanism. And then they saw in CT that how microcrack density changes after and before exposing to cyclic loading.
Oh,
Yeah, but we
okay.
didn't do CT. Yeah.
Yeah. Okay. Thank you very much. So Alireza asked, in your triaxial test, did you account for actual pore pressure, or the sigma 1 is somehow a proxy for cyclic pore pressure? If you inject any fluid, is it single phase or two-phase geomaterial?
Yeah. Yeah, that's. I assume he asked it for first part of the setup. Yeah, it's definitely really nice question, because we always let's say try to mimic cyclicity, because in your real reservoir you inject and you take it out, and then by changing in the pore pressure you change effective stress by assuming Biot coefficient 1. Here we did the same. We kind of mimic cyclicity by increasing axial stress in our setup. Our samples are, I mean, just water saturated, no other fluid. Even for my injection, my one that faulted when I showed, it's just water, just a single phase tap water. But that's of course super interesting to go for, yeah, let's say a mix of fluids and then see other effects for sure.
Okay, thank you. Another follow-up question by Alur is, do you expect different behavior for other rock types? Like, for example,
Yeah, definitely. Yeah, definitely. Because even in the sandstone, not just even changing the whole rock type, even in the sandstone, we observed if you like take one sample with higher porosity and higher clay content, then you are inducing more deformation in your reservoir. And then for carbonate, depends on their porosity. Yes, it's gonna change. Yeah.
Okay, thank you very much. If the people in the studio don't have any more questions, maybe we can close the session. But before that, don't forget to mark it on your calendar. We're gonna have 2 other amazing talks next week. Next month. And yeah, and I wanted to note that Interpor 2024 is also is open for registration, and you can submit your abstract for both posters and also online presentations. You can check it out as well. Thank you very much, everyone, and have a great day, evening, and morning all over the world. And see you next time on the Porsche Media Tea Time Talk. Thank you.
Bye. Ciao.